Okay, good. That was basically it. It's supposed to be like 10 minutes. I was paying attention because I thought we would have to complete. It depends on your TA. It depends on your TA. They just give you whatever they want. For what? For the leadership class, job class.
So,
Like
here we have a busy week, right? A very busy week. We have quiz Wednesday, Thursday. That's going to happen at the beginning of the session, so don't be late. It's the same thing, half an hour quiz. I looked at it, I didn't write it, it's very easy. It'll be done in 10 minutes. Okay? Like usual, we're going to discuss during the quiz. If you have questions, we want to clarify the questions. There's no problem clarifying the questions so that you focus on the solutions and not actually understanding the question. We have a midterm Friday at 6 p.m. There was some complaint or some question of somebody didn't knowing that there's a midterm on Friday. Okay, I think it was very clear from the beginning of the term that we have a midterm on this Friday. And we have review sessions. Were those announced on Piazza?
Yeah.
Thursdays and when?
It was Wednesday, Thursday, and Friday.
Okay. So you can go to either one of them. I think they've been announced. What kind of material will be presented? Midterm version B, midterm version A, things like that, correct? There is one Thursday at 7:40 p.m. One of them. That's me. So if you like me that much, that you want to see me in the review session, that's the one. If you don't like me that much, you go to the other four. They're going to be roughly the same. I'm not going to do any honors thing during the review session. The review is purely focused on the midterm. So as a result of that, no office hours. So I don't have office hours that day because I'm going to do the review sessions. Okay? I'll answer during the review sessions. I'll have some problems, the midterm version B, but I'll also answer any other questions related to the material for the midterm. The quiz is from quiz 1 material. So what do we have for the quiz? What is the material from quiz 1? You should definitely see in there binary, logic, what else? Combinations. Right? Graphs, perhaps not that much, right? Graphs were in quiz 1. I wouldn't say there's zero chance to see graphs. I'm going to say there's probably not going to be focused on graphs. But we'll see induction, right? Sums. So that is quiz 2. We're not going to be focused on the proofs and the graphs, but we're going to be focused on everything we've seen. And be careful that induction, binary, and logic, all that, like how this number looks in base 4. You're definitely going to see that sort of question. How to transform a base from base 16 to base 8 to base 4, so on and so forth. Okay. Midterm is everything from the beginning of the term. So everything we've done, except some topics that are out. I don't think we cover strong induction for the midterm. Is that declared that there's no strong induction in the midterm? Is it or not?
I think it is, yeah.
I think topics are announced. I think strong induction might not be in the midterm. Okay. With that being said, what's going on today? The regular sections are moving on to the next topic. That is algorithms. We are not moving on to the next topic. We'll do that next Tuesday. So Tuesday we're going to have to play a little bit of catch up with the regular sections because there will be a lecture ahead of us. All right? The reason I'm not doing that today is because that's not in the midterm and not in the quiz, number one. So there's no homework this week. So you submit this homework 6, right? We played, all of us played with limits yet for homework 6, problem 4, right? So we'll submit that, but there will be no homework for next week. So the next homework that's on algorithms is totally fine to wait for next Tuesday because there will be no homework for Tuesday. There's also no online homework this week. So we don't need to study a new chapter right now that's not relevant for the exams, quiz, and midterm this week. That's why I'm not moving on to that. Therefore, Tuesday will be a marathon of catching up with the regular section. No big deal for us. So what do we have to do today for the honor sections? I want to do some more fancy honor stuff that we started last time. And I want to do some problems that are back on the induction recapping for the quiz and midterm. Things like Fibonacci numbers that I started, I'm going to continue for another 20 minutes, are not part of the midterm. The simple version, it is, but beyond that, you're not going to get anything with it. So that's what I'm going to do. Here's what we do. We do Fibonacci. We do the Harmonic Series and some other induction problems. Another thing very important for you, Wednesday, Thursday, for the honors, bring that paper back. Bring paper from last week. We're going to need that paper. There'll be no other printout. After the quiz, we have half an hour. There'll be no additional printout, so you have to bring the paper from last week with you. That's the one we're going to continue after the quiz. Now, in that paper, there's a bunch of easy questions in the beginning. You should do those before the quiz because your induction in the quiz might be similar to one of those. We're going to talk after the quiz about the more interesting questions, the one with circles and triangles and trees, and the ones at the end. So first thing for today is Fibonacci numbers. As a recap, here's the numbers. So the 0, 1, 1. The principle is that we're adding up the previous two, starting at n equal 2. So this is the sum of the first two. This is the base of the Fibonacci, and then sum is 2, right? 3, 5, 8, 13, so on and so forth. That's the Fibonacci number. So we've done a bunch of things. I'm going to recap those things without doing them again. What we've done for Fibonacci numbers is to say we believe Fn is approximately some exponential, x to the n. Approximatively meaning is not exact. We cannot find an exponential to have this property, but the growth, what I mean here is growth is exponential. You're going to need this kind of guess in computer science when you deal with asymptotic running times. I have an algorithm and I does certain things. I want to know how long it's going to take. I don't care about the exact time in seconds. I care about that growth of the algorithm in terms of the input. Is it linear or quadratic or logarithmic or what is it? As in, if I sort n numbers as a function of n, how long is going to take? Is it n squared? Is it linear? Is it n log n? That sort of thing. So if we make this guess, the equation fn plus 1 is fn plus fn minus 1 becomes approximatively x at n plus 1 equal to x at n plus x at n minus 1, which if I divide with x at n minus 1, I get x squared equal x plus 1. Now I solve this equation, right? There's two solutions for it. It's a quadratic equation, right? It's either this value phi, that's called golden ratio. And this is 1 plus square root of 5 by 2. And the other option is the complement in the sense of the quadratic form, that is 1 minus square root of 5 by 2. And the exact formula, once we have this growth, is Fn is phi at n minus phi bar at n divided by phi minus phi bar, which is 1 plus square root of 5 at n, or by 2 inside there. Minus 1 minus square root of 5 divided by 2 by n, divided by the difference between them is square root of 5. So it's very nice, it's a closed form. Of course, if phi and phi bar satisfy this equation, we have that phi square has to be phi plus 1, and phi bar square also has to be phi bar plus 1, simply because they must satisfy this equation right here. They're the solutions for this equation. And we prove this by induction. Last time in class, we proved this formula with base cases and everything else we need. We say it's not exactly weak induction because the actual step was if Fn is phi at n minus phi bar at n divided by phi minus phi bar, and Fn minus 1 is phi at n minus 1 minus phi bar at n minus 1 divided by phi minus phi bar. So I need both of them. Then Fn plus 1 is phi at n plus 1 minus phi bar at n plus 1 divided by phi minus phi bar. So it's not just from n to n plus 1. I need the formula for n and n minus 1 to get to n plus 1. That makes it a strong induction. Strong induction is the ones that we use all kinds of previous statements, not just the last one, to get to the next one. Weak induction is always n to n plus 1 or n minus 1 to n. Everything that requires more than just the immediate last one is strong induction. So we've done that. And that's where we were. That's what we proved. I think I posted a few exercises related to Fibonacci numbers. Those are simple induction exercises. Some of them result from the formula direct without knowing the closed form, just the recurrence. This is called recurrence. And you're going to see a lot of more recurrences in computer science. You can prove some stuff about Fibonacci from the recurrence, or you can prove it from the closed form. Now that you know this is the equation, plug in the equation, you get the answer. So what I want to show you about a little bit what this golden ratio is. I think that's not necessarily very mathematical, but it's a cool thing to know. Here's how you can think of this golden ratio. This has to do with the printing formats. That this is a sheet of paper, right? It's called a US letter format, right? Those papers have the property that the next one, the next size, this is what is it? 11 by 8.5 or something like this. It has the property that if I put two of them next to on this side, right? Then I get the next size, right? And if I put two of those next to each other, I get the next size. So how does that work in terms of the Fibonacci numbers? Here's how it works. If I start with 1 and 1, this is our squares, right? So this is 2 squares. This side now is what? Is the next Fibonacci number, is a 2. So I'm going to draw a square here that's a 2. Right? Because I've got 2 squares of 1, the size is 2. There's the next Fibonacci number 2, I draw subsquare 2. Now, how about this size here? What is this size? That's 1 plus 2, that's 3, right? So I can draw a square here that's of size 3. Now, what about the 3 plus 2 size? That's 5, right? So I can draw a square here that's of size 5. I could have drawn it here if I wanted to. So I'm marking not the area, I'm marking the side. How long is the side? That's a 5, right? So now, how much is this 5 plus 3 here? Is the next Fibonacci number, right? So this 5 plus 3, you can draw it anywhere you want. You can draw it here. That's the 8. Or I can draw it here. That's also an 8. Because it's 5 plus 1 plus 2, that's 8. Right? So then what about the 5 plus 8? That's the next Fibonacci number, 13. So that will be a square of size 13, right? Where is the next size? 13 plus 8, that's a 21. So that's how printing sizes work. The printing sizes have this golden ratio in between them. The length divided by the width of the paper is the golden ratio, is this phi, 1.68 approximately. So they have this property, easy to cut from a big sheet of paper, to cut all those sides, because you follow these cuts in here. So this kind of geometry follows the Fibonacci number. They occur naturally in this problem, and I'm going to give you another example right now, why Fibonacci numbers occur so naturally. Here's an example. Let's call it exercise. Count bytes. Bytes are a sequence of how many bits? 1, 2, 3, 4, 5, 6, 8 bits. So bytes is 8 bits. With the property do not contain consecutive ones value. So I want to know, how do I compute the number of bytes, aka sequences of 8 bits, that are not allowing to have ones one after the other. So for example, valid ones would be things like 1, 0, 0, 0, 1, 0. 1, 0, is that valid? Yes. How about 0, 0, 1, 0, 1, 0, 0, 0, is that valid? Using the string again, right? Let's put it down. How about invalid ones? Anything that has two ones next to each other is invalid, right? 0, 1, 1, 1, 0, 0, 1, 1, 0. That's too many? Yeah. 0, 0, 1, 1. Anything that has two ones next to each other is invalid. How do I do this? I can grind all possibilities because it's only 8 bits, right? I can just play with cases. If the first one is a 1, I have here a big tree in my paper here. So you start with a 1, right? I can do the brute force solution for this, which is if I start with a 1, what do I have to do? I have to put a 0. Now that I put a 0, I can do whatever I want, right? I can either put a 1, and then if I put a 1, I have to put a 0 because there can't be two consecutive ones. But if I put a 0, I could put either a 1 or a 0. And of course, I could start with 0, and then I can do anything I want, 1 or 0. But of course, if I get a 1, I get a 0. And I have to build this until bit 8, right? I have to build this tree going out, all possibilities to see what I get, and then at the very end count all these possibilities. It's a brute force because it's essentially listing out all the possibilities. This is a little smarter here. It groups the final sequences into categories to count. That's not the solution we're interested in here. All right? But clearly, because there's only 8 bits, it will only take about a few minutes to write this up to the 8-bit and then count how many things you have. Here's how I want to think about this problem. I want to think in the following way. I look at the byte. I want to do this for the first, this split into 0 and 1 for the first bit. So valid byte is the one that has this property, right? It doesn't have two consecutive ones. If I start with a 0, how many bits I have after that? 7, right? What can I tell about these remaining 7s? So if I start with a 0, in how many ways can I put 1s and 0s to make it valid here? I'm thinking about the recursive thing. I'm saying, let's count the valid bytes on 8 bits. I'm going to call this count C8. C8 stands for how many valid bytes, valid meaning not repeating once, not consecutive ones, can you do on 8 bits, right? But if I declare it this way, who's going to be C7? Like the same thing, just not on 8 bits, but on 7 bits, right? So valid 7 bits sequence. And who's going to be C9? Valid 9-bit sequence. So in general, let's just say Cn is the number of n sequence bits, so n bits without consecutive ones. So obviously, all those sequences Cn starts either a 0 or a 1, right? If we start with a 0, what is this? This is a valid sequence of size. So I started with n, now with 8. That will be a valid sequence of n minus 1. Can I say any valid sequence of n minus 1? From any sequence of n, if we start with a 0, that's any sequence of n minus 1 that's valid. What about if I start with a 1? What happens next after the 1? I must have a 0 after the 1, right? Why I can't have a 1? Being invalid, right? Hands up who's with me. Good, so this must be a 0. Must. I can't avoid that 0 if I start with a 1, because if I put another 1, that's invalid. So then what happens in here? What is this? This got to be a valid sequence. It can't have consecutive ones in it, right? And let's write that down. This is a valid sequence of size what? Is it any valid sequence of size n minus 2? If I have a 1 and a 0, the remaining could be any sequence that doesn't have two consecutive ones. So what I want to apply here, go all the way to lecture 1. Remember? The sum rule. I want to count all these sequences. Can I count the ones here and the ones here? What is required in the sum rule when I split into cases and say, hey, you want those valid sequences? Either of that type, 0 type, or they are of the other type, 1 type. I break it into, fork it into classes. What are the requirements to apply the sum rule? There are 2 requirements, right? Yes.
You have to take into account that you're counting something twice, so you have to subtract those.
Right, so what he's saying is, to apply the sum rule, you can't have stuff overlapping between cases, right? You got to make sure the intersection of class A, class 0 in my case, and class B don't count anything in common, because those will be counted twice, right? Remember that? That's in the midterm, right? Good. So, is that the case in here? Are those categories disjoint? Is it anybody that's in here can also be in here? Why are they disjoint? Why no sequence of valid bits can be both there and there?
We can't both start with 0.
Yes, again.
Because your starting point is different. You
Right.
start with 0.
If this was start with 0, this was start with a 1, you can have the sequence in both categories. Right? And there was another requirement for some rule. Not have overlap, and what's the other requirement?
Cover all the cases.
Make sure you count everything, like you don't miss, because you have case 0, case 1, you just miss something, because that's neither case 0 or case 1, right? So, is it the case that I'm covering everything here? Any sequence that's valid is going to be in one of these two categories. Actually, any sequence of any kind will start either with 0 or 1. Right? So, to apply the sum rule, I have to have count everything, not miss anything. Sequences. So that's part number 1. And do not overlap. That means count twice, or more than twice if I have more cases. Those things apply, right? So I'm going to say, okay, Cn, then if the sum rule applies, it's how many valid sequences of size n minus 1 I have. That's exactly Cn minus 1, right? By definition, this number of sequences that I can put here is the number of valid sequences of size n minus 1. That's Cn minus 1. And the sum rule gives me a plus, will be the sum of n minus 2. That will be all the sequences that are in this case. Now, of course, this from here, it's obvious that's a Fibonacci number. I have to verify base cases. These will be Fibonacci numbers, given the recursion is the same exact recursion like Fibonacci, it adds the previous two. We only need to verify that the base is the same, because I can build the same recursive values, but not starting from 0, 1, right? I can start with 1 and 3, and then I get a different sequence, right? 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 4, so on and so forth. So to verify that this is Fibonacci, we got the recurrence, that's the hard part. But then now we have to verify, is it really starting with 0 and 1? Is that the case? Right. So that's up to you guys to verify. I think the actual value is Cn is Fn plus 2. It sums the previous two values, but the first one, C1, starts at here, F3. Right? C1, how many sequences have 1 bit? Don't have consecutive 1 bits or whatever.
2.
Which are those?
0.
And what's the other one? 1. How about C2? What are the sequences of 2 bits without 2 consecutive ones? 0, 1, 0, 0, 1, 0. So this is F what? 3? 2 sequences, and 3 is F. So they are the Fibonacci numbers, but not starting from 0. They start from here. And then, of course, because of this pattern, they follow the Fibonacci numbers from there. Okay. So you can see how this shows up naturally and other recurrences like this in problems that don't even mention anything with addition of previous two. Like to get from this problem to the Fibonacci numbers, someone has to figure out, hey, there's a sum rule there that applies and da 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 da. The problem itself has no hint at why would those be Fibonacci numbers. Right. Here's the same problem written a little bit different. I mean the same way of reasoning. Decompose n into a sum of 1 and 2's order matters. So as an example, n equal 5, I can write 1 plus 1 plus 1 plus 1 plus 1, 5 ones, right? I could also write y plus 1 plus 1 plus 2. This would also be 1 plus 1 plus 2 plus 1, or 1 plus 2 plus 1 plus 1, or 2 plus 1 plus 1 plus 1, or 2 plus 2 plus 1, or 2 plus 1 plus 2, or 1 plus 2 plus 2. If I want to break up a number into sums of ones and twos, notice that the order matter is not just the count. I'm not saying between this one here and this one here, how many twos I have and how many ones I have. 2 twos and 1 1. How about here? 2 twos and 1 1. I'm counting this as different summations because the order is not the same. There is a difficult problem that has to do with in how many ways can you break a number into partial sums, not just ones and twos, where the order doesn't matter. AKA 1 plus 2 plus 3 is the same as 2 plus 1 plus 3 is the same as 3 plus 1 plus 2. That has to do with Catalan numbers, that problem. This problem is much simpler on 2 counts. First of all, it only wants to break into ones and twos, not other values. And the order matters. So 2 1 2 is different than 2 2 1. This problem is the same as this problem. Just a little bit of morphing a one-to-one map between them. Here's the deal here. Of course, the question is how many ways, right? How many ways to decompose n into? How many such decompositions are there? So let's call these values dn. How many decompositions are there? Right? And then say, okay, what's up with dn? dn either starts with a 1, right? If it starts with a 1, what is the rest? It's a decomposition into ones or twos of what value? Not dn minus 1. I'm decomposing, I'm decomposing n here. So I'm writing n as starts with 1, and then what's the remaining of this thing? This is going to be n minus 1, right? Or I can start with 2 plus decompositions into 1 and 2 of what value? Now, how many of these guys are there? How many decompositions of n minus 1s into 1 and 2s? In how many ways can I take the value n minus 1 and decompose it as a sum of 1s and 2s by definition here? This is dn minus 1. And in how many ways I can take n minus 2 and break it into 1s and 2s by definition? D of n minus 2. Now, can I apply the sum rule here? Is it any decomposition of n going to start either with 1 or with 2? And I'm not going to count anything twice in here. Why I'm not going to count anything twice? Yes?
It can't start with both 1 and 2.
Yes, but that's because the order matters, right? If the order wouldn't matter, I'm going to count a lot of things twice. But if the order matters, 1 plus cannot be the same as 2 plus, because the first value in 1 is 1, the other one is 2. So then dn has got to be dn minus 1 plus dn minus 2. That implies a Fibonacci sequence. But you can take it home and check the base. Again, a Fibonacci sequence doesn't mean it starts at 0 or 1. Could be starting from somewhere else and still be a Fibonacci sequence. How many people with me so far? Good. So a lot of interesting problem with these Fibonacci numbers. And I have another one. That's not really a problem. that has to do with another way of computing the Fibonacci number. So somebody figured out, hey, here's a cool fact. Here's another exercise first. That's for you to take home. Very, very easy. Limit of n goes to infinity of fn plus 1 divided by fn is that golden ratio. That's extremely easy to prove from the closed form formula. You replace fn plus 1 and fn with the 1 plus square root of 5 at the end minus da 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 and try to figure out that limit. In that formula, this becomes irrelevant because the absolute value of this is between 0 and 1, right? When you raise it as a power of n, it's getting 0. So then I'm left with this as a dominant term, and you can easily see why if I do n plus 1 divided by fn, the limit of that will be 1 plus square root by 5 divided by 2. But you can try that. But more importantly from here, the growth is exponential, the approximative p to the n. The limit, this is a property of limits if the ratio between the consecutive terms of the sequence becomes close to a constant, it has a limit, say the constant is 3. Then the sequence itself has to be about 3 to the n, so that the limit between the next guy and the previous guy, the ratio, gets to be about 3. Right? So here's what I want to show you here. It's an enormously important fact for computer science. Somebody figure out, do we remember matrices? This is a vector of what size? How many rows and how many columns?
2 rows, 1 column.
2 times 1, right? This is the following matrix, 1, 1, 1, 0, times fn minus 1. Is that working? So this is 2 by 2 and this is 2 by 1. What property do I need to multiply matrices? There's something to do with rows and columns that otherwise it doesn't work, right? Anybody remembers that? Yes.
The columns of the first one is equal to the rows of the second.
These 2 has to be the same as these 2 here. Otherwise multiplication doesn't work, right? So it is. So, and the result, if I multiply them, that 2 goes away and I get the number of rows from the first one, number of columns the last one, that is the 2 by 1 here. So this is a matrix multiplication. Is this true, first of all? We can verify, well, is it or not? What is this? So how do I do this multiplication? Anybody remembers? Yes.
So
Take the first row.
take the first row, transpose it, and do the dot product.
Multiply with this column. So that is fn plus fn minus 1, right? Take this row and multiply it. And the last one is take the second row and multiply with the column, right? So that is 1 times fn plus 0 times fn minus 1. Is this that thing here? This is just fn, right? And this is fn plus 1 due to the recurrence of the Fibonacci numbers. The sum of 2 consecutive ones is equal to the next one in the sequence. Very easy, correct? Well, the advantage of this is that I can then say, fine, then how about I say, let's call this matrix Rn. This gives me the formula Rn as a matrix is 1, 1, 1, 0 times Rn minus 1. Right? Because if this is Rn, this here is Rn minus 1. So that implies that Rn has to be this matrix 1, 1, 1, 0 n minus 2 times R2. I guess I can go to n minus 1 times R1. R1 will be defined here. If this is R1, well, let's see what I get. Okay, I think I might have gotten this wrong a little bit. We need another matrix equation here. Before we get into this, that's going to happen, but this is not the matrix Rn. We need another formula. So this is just doing this one here, but doing it twice. So you can see this column here is this one here, and this column here is this one here. So how do I get the first column? I apply the first equation, and I get this matrix multiplied by the first column. Now what about the second column? The second column works in the same exact way. The second column, this, is the whole matrix times the second column here, which is the same equation just for n minus 1, the previous n. I want to make sure we all understand this. Assuming we all process the first equation, can I apply that equation separately for the first column and then for the second column of the matrix? Hands up, who's with me? Right. So we can verify this manually. That's the same we did that one. That would be another way to check it. How about we do that? This is how many computations I have here. I have 4 computations, right? Because 2 times 2. So 1, 1 multiplied with fn and fn minus 1. I get fn plus fn minus 1. The same row times the second one will be what element? If I do the first row times the second column, where is that in the result?
First row, second column.
So that will be who?
Fn.
F. I'm multiplying the second column.
Fn minus 1 plus fn minus 2.
And if I do now the last row times the first column, I get fn. And the last row times the second column, I get fn minus 1. So I can verify that this is the matrix here. Right? But it's the same as doing column by column the first equation. Now I call this Rn. This is the Rn that I need. So erase what I wrote a minute earlier. And this is Rn minus 1. So Rn is 1, 1, 1, 0. That's a fixed matrix times Rn minus 1. That implies Rn as a matrix is 1, 1, 1, 0 at the power n minus 2 times R2. Because what happens here, to move from one Rn to the next Rn, you multiply with this matrix, right? So inductively speaking, this would be 1, 1, 1, 0 at power 2 times Rn minus 2. That will be 1, 1, 1, 0 at power 3 times Rn minus 3. Eventually, it's going to be that. Because every one of these R's matrices is this matrix multiplied with the previous one. So it's just the base one, say it's R2. R2 is nothing but who? R2 is F3 or F2. F3, F2, F2, and So here's the deal. Why is this important? One can compute the Fibonacci numbers this way, right? One can say, just take this matrix, multiply with this matrix at the power. So this is a base matrix, and multiply with, depending what Fibonacci you want. If you want F100, you're going to have to multiply with this matrix at power, I don't know, 98 or something like that. If you want F1000, you take the same matrix, multiply with the matrix, this matrix that's a fixed matrix at power 998, right? And I can get a matrix with 4 values. In these 4 values, I get my Fn here or here, and this is the next one, this is the previous one. How many operations would it take to multiply this matrix with itself n minus 2 times? That's the key. Because alternatively, someone else can do the following. Someone else can say, why do I complicate myself with those matrices, right? Can I write a quick program to do Fibonacci? F0 equals 0, F1 equal 1, 4. You guys seen this kind of programs written on the board? Anybody knows how we call them? They're not really programs. Pseudocode, right? For k equal 2 to n, right? What do I do? Fk equal, how do I get the next Fibonacci number in my program here? Yes?
F of k minus 1 plus f of k minus 2.
That's why I started from 2 to have F0 here, right? And then I'm done with this 4. I can say N4 if I want to here, right? To mark in my program. This is not really a programming language, it's Virgil's language. Everybody has a different pseudocode, and that's fine. Pseudocode are for you to think through the program. It's not a universal pseudocode language. And then what do I have now here? I just have output Fn, right? How many steps will take this program, roughly speaking, in terms of n? Is it a linear program? It takes roughly n steps, apart from the initialization here. How many times this for loop gets executed? N minus 2 times, right? Or n minus 1 times. That's roughly n. In complexity, how long does it take? We say that's a linear. And inside, how many operations are inside? 1 operation. So it's roughly n steps, or n minus 1 steps, times 1 operation inside the loop. That's roughly, we call this O of 1. That's from 1 operation, times O of n. This is linear. It's really n minus 1, but we say roughly the complexity is n as opposed to say n squared. That will give me O of n runtime. How would I write this program? If I write program that do that, how would that look? I'm going to write it right here. Start with this matrix R2, which is whoever, F3, F2, F2, F1, something like that. I start with that matrix, this one here. And then I say for I equal 3 to n, compute Ri or Rk, let's do k again, k. Rk is 1110 times the previous R, Rk minus 1, right? That's the recurrence I got here. And then I'm done. And 4. I've got my matrix now, Rn, and who's Fn? Is the second row, first row, second row, first column element in Rn. So once I got my Rn here, I say this is my output Fn. How many steps will this take? Same number of steps, right? It's initialization. This is roughly O of n steps in the loop here. It's n minus 2, but that doesn't matter. Times how many operations are inside. Even though this is a matrix, we still count it as a constant operation. It's 4 operations instead of 1, but that's still O of 1, so that's O of 1. That's still a linear running time because I'm doing n steps, each of them with 2 or 3 operations in them. That counts as one operation. We can call it matrix operation. Here's my point. This is going to be linear, but I can make this faster. There is a way to multiply matrices or anything, multiply this faster than doing one by one. What this does is, if you want this matrix, so how do we compute this matrix M, which is 1, 1, 1, 0, at a power P fast? Same way we can do x to the P fast. The way to do this is not by doing x times x times x times x P times. That's slow. That will require P multiplications. Anybody knows how to do this faster than
Exponentiate it, so you can convert P to binary and just multiply it. It's the only steps.
That's called repeated squaring. So here's how it goes fast. If P is 100, you say convert it to binary, right? So that's 64 plus 32 plus what, 4? Is that right? 100 broken into power of 2. Here's how I can do this much faster than multiplying P with itself 100 times. I start with x, I square it, I get x squared. Square it again, what do I get? Square it again. X to the 8. Right, x4 square. I'm only squaring the previous result. What's the next one I get?
That's the 16.
Next one?
That's the 32nd.
And the next one?
That's the 64.
How many multiplications I've done to get up to here?
6.
1, 2, 3, 4, 5, 6. This is 6 multiplications. Not 63. And now, what do I have to get x at 100? I have to pick some of those and multiply them together. Which ones? X at 64 times x at 32 times x at 4. So how many total multiplications I have here? To get the powers by repeated squaring, how many multiplications I have? 6. And to get this now, how many additional multiplications I need? 2. So I've done the whole thing with 8 multiplications instead of 99. How many people with me on that? This trick, it's extremely good for computer science applications when we care about speed. Of course, mathematically we get the same result. But by doing this, called repeated squaring, I do 8 multiplications instead of 99. This trick applies to matrices the same way. If I have a matrix and I want to raise it at the power, instead of multiplying with itself p times, I can do repeated squaring for that matrix and then just multiply the matrix that I need.
So is matrix multiplication associative?
What?
Is matrix multiplication associative?
As in A times B times C
Yeah.
is the same as A times B times C?
Yeah.
Anybody knows the answer to this question? Is matrix multiplication associative? Can I multiply those two first or those two first? I get the same answer? Yes or no? A definite answer. Anybody knows the answer here? Yes. How about commutative? Is A times B the same as B times A? No. Yes. All right, so that's what I have for Fibonacci numbers. And we've done a lot of Fibonacci numbers now. The other thing that I want to do here today is to talk about one particular sequence or series that is significantly more difficult than arithmetic, geometric and quadratic. Those are the three sequences that you should expect in the midterm. If you in the midterm get a sequence that it doesn't appear to be geometric or quadratic or arithmetic, you can be 100% sure you did something wrong in your calculations. Because the midterms in the sequence will be one of those three. I mean, I hope that's clear by now. That if you do something that doesn't appear that way, then you must have a bug somewhere. But now we're gonna do talk about harmonic series, which is 1 over 1 plus 1 over 2 plus 1 over 3. We just call it Hn from harmonic plus 1 over n. And I already told you that this is roughly natural logarithm of n plus a constant. The constant is given somewhere. We have it here. We used to have it here. Not important for us right now. This is called the natural logarithm. It's log base e. Right? It's a very important number, e, in mathematics. So how do we get to here? So there's some simple exercises. Prove that Hn is divergent, meaning without logarithm approximation. That is the limit when n goes to infinity of Hn is infinity. That is not a trivial question. It is true that this is an infinite series. It adds up terms after term, but each term becomes very, very small, right? So even though it's an infinite series, the question whether it's convergent or divergent, it's pertinent because the terms that are being added are getting smaller and smaller and smaller. In fact, they go to 0, right? So the Hn plus 1 minus Hn is 1 over n plus 1, right? Is the difference between the two sums. The limit of this is 0. So what I'm adding from 1 Hn to get to Hn plus 1, it's a quantity that gets smaller and smaller and smaller. If this quantity will not go to 0, it would be always bigger than, say, 0.5. Of course, the series will be divergent, right? If you keep adding 0.5 or more at every step, and you add infinite number of steps, that 0.5 adds up infinite number of times, gets to infinity, right? But in this case, what I'm adding up gets very close to 0. So it's possible to add up infinite amount of terms and not diverge, not get to infinity. There was a question in the recitation about this, right? Remember that question? That was saying, what was it? 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squares plus. All of them, it's smaller than 1. If you add all of them. This is your recitation paper from last week, right? We did it in class with some trick, with some approximation, with arithmetics. The point is, see, that's the same infinite, it's an infinite series, so I'm adding an infinite amount of terms here. But because the terms are so small, they're getting so small, I can't beat a certain value. They're not going to infinity, the sum, because I'm adding very little. Another infinite series that you've seen is the progressions of 2. 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 2 to the k plus. If I add up all these terms, all of them, infinite, right? There's infinite number of terms in this sum. What do I get? 2. It's another example of an infinite series that have an infinite number of terms. But each term gets so small that when you add up all of them, you don't get infinity as a quantity. It's actually getting stuck at 2. It can't be 2. Right? So these are all positive series. They all add a positive quantity. The question is this positive quantity that goes to 0 it's going, how fast is going to 0? In these cases, the positive quantity in here is 1 over n squared, right? That's what's being n plus 1 squared. The delta. And in here, the delta is 1 over 2 to the n plus 1. These deltas between the series and the next n series are going very fast to 0. They become very small very fast. Therefore, when you add them up, you don't go to infinity. In here, they do go to 0. The delta does go to 0. It's 1 over n plus 1, but not fast enough. Still, if you add up all these values that go close to 0, the result is not convergent. It's a divergent series, meaning it goes to infinity eventually. So you can see this, if you use the logarithm approximation, that's obvious, right? Logarithm goes to infinity, correct? So if this is logarithm plus a constant, and the logarithm goes to infinity, that has to go to infinity too. No doubt about it. But there are a bunch of elementary proofs why this has to go to infinity without using the logarithm approximation. So there's people, for example, I'll do a schematic proof here that says, here's how you can think of this. H1 is 1 plus 0, 1/2. H2 is 1 plus 1, 1/2. H4 is 1 plus a half plus a third plus a fourth. It's bigger than 1 plus a half plus a fourth plus a fourth, because 1/3 is bigger than 1/4, right? So I'm getting 1 plus 2 halves. And then H8, it's 1 plus 1/2 plus 1/3 plus 1/4. This is the same approximation as before. Plus 1/5 plus 1/6 plus 1/7 plus 1/8. I'm grouping those. This is 1 plus 2 halves from here. Plus, I'm replacing those, all of those terms with 1/8. So that gives me 1 plus 2 halves, 3 halves, essentially, right? 4 1/8 is another half. So by doing this, by induction, I get F, this H, every time there's a power of K, is going to be bigger than 1 plus K times a half by induction. This is induction exercise. Now this tells me that eventually, 2 to the K is a very big index, of course, but eventually you can see that this is going to go to infinity because it's K times a constant. So when K goes large, this value is not bounded, can't be below any fixed threshold, right? How many people follow this? Because I'm not doing every HK, I'm doing every H2 to the K. So it's really have to go really far away in the sequence to prove divergence, but I can go really far in the sequence that I want. So that's going to go to infinity. So there are elementary proofs that show divergence without the logarithm, without mentioning the logarithm word at all. Our interest is, however, is this approximation that's important in mathematics and important in computer science. Why is this roughly the logarithm plus a constant? It's a key thing that opens the gates of calculus. That's where calculus starts. And I know you've done calculus with formulas before, but typically in high school there's not a lot of calculus reasoning with limits and such. And this is where the discrete math ends and the calculus starts at this limit. Okay? So you have something in the recitation paper that is an inequality that we want to prove. The inequality we want is, this is a fundamental inequality that gives the first limit in calculus, which is E. 1 over n plus 1 is smaller than natural logarithm of 1 over n smaller than 1 over n. This is what we want. And the exercise in your recitation paper to get there, this is recitation, says you have to prove this. Anybody looked at this problem? I think somebody, this is trivial. I mean trivial. Right? This inequality in the middle, it's simply the fact that these have the same base and the right one is a bigger exponent. Yes?
Could you make that a little bit lower? The bar was kind of in the way. Thank you.
So this is in the recitation paper. 1 plus 1 at the n to the n is bigger, smaller, smaller. 1 plus n plus 1 at n plus 1 smaller than 1 plus n plus 1 at n plus 2 smaller than 1 plus n plus 1 over 1 n at n plus 1. Right? This is obvious, the middle one, because these two have the same base, just a bigger exponent on the right side. So that's no problem. Somebody at office hours proved this. Does that work out? Did you check it? I think you did with me some help in there. But we don't have this yet. That's in the recitation paper. You can attempt a proof by induction, but these proofs are a little difficult. Now, I won't do that right now. I'll leave this still for people to struggle with if you want to. Is there an easy way to get from this to this? Like, okay, assuming somebody smart can prove these three inequalities. How do we get from here to here? Is that what I want to show today is that if I knew those inequalities, I get this one. I say that's not hard. So how about if here I take logs of all that? What happens when I take logs of this inequality? What is log of a at power p? How does logs deal with the power inside the log? Huh? Jumps in the front, right? It's p log a. So then if I take the logs, this becomes n logarithm of 1, right? This is smaller than n plus 1, the second one. Logarithm of 1 plus 1 over n plus 1. Smaller than this one is n plus 2. Let's say ln. I want to take the natural logarithm to get that in one shot. ln of 1 plus 1 over n plus 1. Smaller than the last one would be n plus 1 natural log of 1 over 1 plus n. So how this worked? Every exponent jumps in front of the log is the log of the remainder. So now, where is this inequality? It's now with equal signs. It's without equal signs. Where is this one here? Do I have this one here? So this in here. 1 over n plus 1 smaller than this. I say both inequalities are somewhere in here. Just have to figure them out where they are. Yes.
The properties of a logarithm, like the inside parts, you can take it as ln of 1 times ln of 1 event, like 1 over n, and ln of 1 is 0. Or,
Which one? This?
yeah, or, never mind, I have that backwards.
Yeah, I think he's right. The other property that we need is log AB is log
Of
A plus log of B. So what I'm doing here is, assuming I have the inequalities at the top, can I conclude this? No? So let's take this one here. Where do I get this? Just this part. What is this equivalent to if I move the n plus 1 in here on the right side? This in here is equivalent to saying 1 is bigger than n plus 1, right? Natural logarithm of 1 over n. Where is this n plus 1? It's right here, right? Isn't this bigger than 1? Like one of these terms I can get somehow bigger than 1? Okay. All I need is this bigger than 1. But why do I know that this is bigger than 1? How about we leave it here to see if somebody figures it out by tomorrow as recitation. This first problem I want to talk about is recitations. If somebody gives me this inequality, where do I get the log inequality? So I take the logs, of course, I get this. And now this term here is this term here with n plus 1. Why is this bigger than 1? Why on the other side I have a 1 if I want to? And this one here, the other inequality, if I move the n, what is this equivalent to? N times log of 1 plus 1 over n is smaller than 1. Where is that coming from? So maybe you guys can work on this if you have time, and our recitation will have an answer. What I want to do after leaving you with this is to cheat a little bit. I'm cheating in the following sense. Calculus is not possible without this limit. Everything you study in calculus relies on this limit. So if everybody tells you I'm doing anything with calculus, differentials, integral, limits, they must have this limit in the bag first. So I'm going to cheat on that. I'm saying I'm going to assume that I have calculus in my bag, right? But somehow I still want to prove this limit. That's of course impossible because to get any results in calculus, we need this limit first. But I'm going to go around and say, I'm coming from a different planet where we figure out calculus somehow without this limit. So here's how I'm going to prove this inequality with calculus. I'm going to say, somewhere in here, here's an inequality. 1 This is obvious, right? If x is from 1 to 1, that means 1 is smaller than x, smaller than 1 plus 1 over n. When I reverse all the quantities, right, I get 1 over 1, 1 over x, 1 over this. But I also reverse the inequalities, right? Because if a is smaller than b, then 1 over a is bigger than 1 over b. You guys following me here? So what I'm going to do, I'm going to integrate this function. I'm going to say, okay, if this is the case, then the integral from 1 to 1 plus 1 over n of this quantity 1 divided by 1 plus 1 over n dt is smaller than the integral of 1 over x dx. It's smaller than the integral of 1 plus over n of 1 dx, right?
You have to change the n in the first integrand to it.
What?
I think you need to change the n in the first integrand.
This n?
Yes.
The n is fixed here.
Oh.
So n is fixed. X is a variable. So you can think of this n as being fixed at 100. So x runs from 1 to 1 plus n, right? So if you look at the real axis, somewhere is 1 and somewhere is 1 plus 1 over n. This is where x is. And x is a variable that goes into this real interval. Now, do we remember from calculus from high school that if two functions, this is a constant function, right? And this is another constant function. So do we remember that if x is in between, the integrals have to work that way, right? The integral of a smaller function is smaller than of an integral of a bigger function than that one. So now I have to compute these integrals. This integral here, it's 1 over n plus 1. This integral here, anybody knows how much to is 1 over x integrated?
That's 1 over.
That is f of 1 plus 1 over n minus f of 1, right? Where f is the function that differentiates to 1 over x, right? So I need to know what function differentiates to 1 over x to do this integral in closed form. And of course, this one here is 1 over n. This is easy to compute. Is the 1 plus 1 over n minus 1. That's 1 over n. So this is where I'm cheating. The integral of this is the logarithm. So if I knew the integral is logarithm and how to integrate functions, I could prove this inequality direct. Of course, that's cheating because you can't even define the logarithm without e. And to get e, we need first to solve that inequality and to prove it around, right? So I want to show you this because a lot of discrete problems like this one or this one could actually be solved or at least thought of much easier in a context of calculus or non-discrete continuous problems. Like in here, in order to get this, even if I'm not allowed to do that proof, the fact that I relate the integrate on 1 over x to the logarithm allows me maybe be able to think better about it. A lot of discrete problems could be solved that way. There is one massive such example other than this one. Which deals with convergence of series. So that one I have a lot of notes in here. Is the integral test. That says if my series sequence is a function of n, then sum from k equal 1 to infinity of ak is convergent, meaning the limit is some L that's a real number, if and only if the integral of 1 to infinity of f of x dx converges. That is, it's finite. Now we're not going to prove this result from calculus, but this is a very easy way to tell for a series if it's divergent or convergent right away, if you know how to integrate it. So for example, that series over there, if an is 1 over n, then that's my f of n. The function f of n, the big function, is the logarithm. The big function has the property df at dx or dn is the f of n, right? The differential. It's called primitive. In this case, the harmonic series, which is the sum of 1 over k, is convergent if and only if the integral of f is convergent, but this integral is ln of x. ln of x is divergent, therefore this must be divergent too. Here's another example. How about the example from the recitation, the n squared? If I'm to sum up n squares, if this is my f of n, what do I need f of n to be? What function differentiates to 1 over n squared? Anybody knows? How do I pick a function that differentiates to this? What's the general formula of inverse x at minus p differential is what? Minus p x at minus 1. So if I want this to differentiate to be n squared, that is n at minus 2, right? What do I need the function to be that differentiates to that? I need some fraction in the front, and then this got to be n at minus 3? No, minus 1. So what do I need in the front? Minus 1? Imagine this p being 1, I get the minus 1 x at minus 2, but I need to get rid of this minus 1. So that is really minus 1 over n, right? True or false? What if an is 1 over n cubed? That is n at minus 3. F of n. What function do I need to differentiate it to that? Minus 1/2 n at minus 2? Would that work? So my point is, if somebody wants to sum up these kind of values, so in here, what do I get? Sum over 1 over k squared. That was the problem in the recitation. Is this convergent or divergent? That gets to be the integral from 1 over infinity of 1 over n, right? Over k squared. So that's approximately 1 over, so these integrals here, this is f, small f, and this is big F of x minus f of 1, limit, and x goes to infinity. So this in here ends up being roughly 1 over n minus 1 over n plus 1, which is divergent, convergent. So I can do a lot of things here that are very hard to do in a discrete sense. Like some of these we can apply tricks like we did a recitation, or proofs like that and get it in a discrete sense. But there's some extremely hard to do. For example, if an is, what's this example here? 1 over n log n. So the sum of ak is sum over 1k log of k from k equal 1 to infinity. Is this convergent or divergent? Notice that these values are all of them smaller than the harmonic series values, because they're not just 1 over k, it's k times something, right? So they definitely smaller than the harmonic series, but bigger than 1 over k squared, right? So I could say this sum is definitely bigger than sum over 1 over k squared, because all the terms are not k times k, are k times log, but definitely smaller than sum of 1 over k, because that's I have another logarithm term at the bottom. So I know this is between a divergent series, the harmonic series, and a convergent series, the 1 over k squares. I proved that at recitation. But is it divergent or convergent? If I sum up all these terms, do I get stuck at the value or I go to infinity? That's an extremely hard problem to do with discrete math. But if I apply my integral test here, all I have to do is figure out which function, big F, differentiates to this thing, right? If I know the function that differentiates to this, I apply the integral test, I calculate, right? So this is the integral of 1 over k log k, would be approximately f, big F of x minus, big F of x minus 1. I have to know what function differentiates to this to be able to apply this test. So I happen to know that function. Right? F gotta be ln of x. So it's a double log function. This double log function, this is minus 0 here, still goes to infinity. It's a very slow function, right? Log of log. I mean, x gotta be a gigantic number to get even 5, right? Of it. Because 2 at 2 to the 5, or e at e to the 5, it's a very big number. But it still goes to infinity. It's a very slow function, still divergent. Another set of very important exercises of this kind are, what about the series 1 over n to the p when p is a power? So an is 1 over n to the p. This is k. K equal 1 to infinity. So we already done p equal 1 and p equal 2. We say for p equal 1, we get the harmonic series. And we know that goes to infinity. And p equal 2, we get 1 over k squared. That's inverse quadratic. We know that goes to p squared by 6, I think. You can compute calculus. It's finite. How about for p between 1 and 2? How about for p equals 0.5? Sorry, 1.5. So that would be, for example, at 1.5, I get the square roots, right? Is the sum over square root of k. If I put in k times square root of k. If I put a p that's between 1 and 2, what happens to this sum? Is it convergent or divergent? Again, another hard questions to ask, hard question to answer with discrete math. But with the integral test, right away, all I have to do is find a big function f that differentiates to 1 over k to the p. Once I have that function, my convergence or divergence depends on whether that function is finite or not, and I'm done. So, do I want to get into calculus? No. This is still a discrete math class, but a lot of discrete math questions relate to problems from geometry and calculus, and you can easily answer them if you know the calculus side of things. Because for some of this, again, it's very, very hard to come up with discrete math proofs, things like induction. I want to post a different one here that's also in your recitation paper. I think this is the last one I'm going to do today. This is a very well-known inequality since antiquity. Since long time ago, people use this inequality. It's called the inequality of averages. The quadratic average is the square root of a1 squared plus a2 squared plus an squared divided by n. This is always bigger than the arithmetic. That is a1 plus a2 plus an divided by n. That's always bigger than the geometric. That's the square root of size n of a1 times a2 times an, square root of order n. And that's always better than harmonic, which is n divided by 1 over a1 plus 1 over a2 plus 1 over n. So you should know, if you want a big average that depends on the big values, use the quadratic one. Like, professor asks you, hey, I'm going to take the average of 4 quizzes. Which average would you prefer? I want the quadratic one, because I only need to do good in 1 quiz to do well. Typically, we use the arithmetic average, right? We average your homeworks, divide by how many they are, right? That's still in your favor. See that that's towards the, the bigger side. The really small average depends on the small numbers. One failure, one small value here, and the whole average goes down. Like, imagine what happens if one of these A's, just one is 0. So you do good in 6 quizzes, but you miss 1. They get a 0. What will happen with this average if one value is 0? The whole thing becomes 0, right? So you only need one value to be small, so the average is small. Right? So you really don't want to be evaluated with the harmonic average. Harmonic averages are good when you want to ensure all values must be high. You can't have a small one. Right? So suppose I want to prove this inequality. I can attempt a proof by induction, right? I'm going to take this one here. How the induction step looks like if I want to prove this inequality by induction. I would need to prove, how do I go, induction step goes from n to n plus 1, right? In here, it's a weak induction. How would I do that? I would say, well, if this is true for n, if the square root of a1 squared plus a2 squared plus an squared by n, it's always bigger than, all these values are positive. It's always bigger than a1 plus a2 plus an divided by n. Then what? Remember, I have to state the step first. How do I write the same thing for n plus 1? Square root of a1 squared plus a2 squared plus, what's the last one here now? n plus 1 squared divided by n plus 1. It's bigger than a1 plus a2 plus an plus n plus 1 divided by n plus 1. That's what I would need to prove if I want to do it by induction. So I have a proof here. It's not looking good, right? And that's the easiest one. This inequality is the easiest out of the 3. But it's doable, right? I mean, what would this mean? Like, instead of doing the induction like I did in class, I'm just going to do a schema here, just really quick. What would this mean? If I take the square roots out, do I get n sum of ai squared from I equal 1 to n bigger than sum of the ai everything squared on this side? If I just manipulate the, I square the whole thing, to get rid of the square root, and then I got an n squared here and an n here, so when I move that n squared here on this side, I only have an n here. This I need to prove that it's bigger than n plus 1, sum of the ai squared, that this is from I to n plus 1, is bigger than sum of the ai, this is from I equal 1 to n, this is from I equal 1 to n plus 1 of ai squared. That's what I need to prove. So I'm at 1 category. Okay, I'm going to work on this one, like with induction steps. We keep working on here. I'm going to say n plus 1. This I want to break not into, I want to break into all of them up to n, I equal 1 to n of ai squared. That's the first one. Plus n plus 1, the last one, which is an plus 1 squared, has to be bigger than this. It's a sum of p plus q, two terms. P is all of them up to n, and q is just the n plus 1. So that will be the sum up to n of ai squared, right? Plus the last one squared, plus 2pq, right? P squared plus q squared plus 2pq. So that's the sum of I equal 1 to n of ai, that's the p, and then an plus 1, that's the q. So what do I know from this? I'm going to break this sum further, n sum of ai squared plus sum of ai squared from I equal 1 to n. I'm going to replace this n plus 1 into n oranges and 1 orange, plus n plus 1 squared plus n plus 1 squared, like that, bigger than this thing. So now what I know by induction hypothesis is that this here is bigger than this here, right? My induction hypothesis is exactly here. So I got that covered. I also can see this an plus 1 squared that goes to the n plus 1 squared, right? So I'm left with, meaning 1. I would like to prove that these two things, sum of the ai squared from I equal 1 to n, plus n plus 1 squared, without the sum, this thing, is bigger than 2 times the sum of I equal 1 to n of ai times n plus 1. Because this, I know it's bigger than this from the induction hypothesis, and this I can see it's being the same thing. I want to prove this. Stuck again. Maybe this is something like p plus q, p squared plus q squared is bigger than 2pq. Is that something like that? Can you find a p and q that just does this for me? Because that would be true, right? Is p squared plus q squared bigger than 2pq all the time for positive values? If I can make this being p and that being q, maybe I can work it out. I don't know. Here's my point about all this. This is extremely hard to do this way. And you can do it just hard. The right way to do this is with convex functions, which we don't know. Right? It's the same like with calculus. If I apply convexity arguments, the whole proof is one line. Right? But I need to know convex functions, right?
Like 20 minutes with how to get the side effects of taking it.
For what?
Like they're not that bad actually. Really, I mean, so long as you don't get dependent on it. What? Yeah, but like, yeah, it's so easy to like. Oh, I see.
Not today. The key is in the shop. So, But if you ask me to do something, I think it's a whole fun. It's not moving between the sections. But if you just go to the other section and go down, Kevin's code has the same. And it's a very good thing. I'm not flexible enough. If you go there and you follow that, you use more of the time for the exam. I have to do this, but I need to go down to the exam. But I need to go. Try it out and see how you feel. Maybe you can try it out just before the meeting.
Same thing happened again. I woke up. This was a review day.
Just don't hold me that day, because I'm not supposed to give you that answer at the same time.
Yeah. You want to try it? Just wait for it.
You guys know complex functions?
I do not. I do not.
Very